Hello, everyone. Welcome to Northwest Michigan Orchard and Vineyard Show. Today, we are going to talk about many good stuff. So, we are going to talk about trunk disease management and also we have a part related to enology. So, we are going to talk about wine canning and a chemical what happened when you put the wine in the can. So I'm really excited about that. And first of all, I would like to say thank you to our sponsor. They financially help us to prepare this program and prepare those goodie bags for everyone. We are going to send some of them for to Canada or other countries. So it's really good. So I would like to remind that Michigan State University providing equal opportunity for everyone, regardless of their differences and their gender or other differences. I'm sure everybody know how to use Zoom, so just I'm going to remind that how you can send your question or note. If you have any question or note, simply you can type your question in Q&A box and chat box and send it for us. And in audio setting, make sure you are choosing right speaker. And at the, my special thanks goes to our collaborator. They also they help us a lot to prepare this program. And at the end of this meeting, I'm going to show RUP credits info. Make sure you write down those information. Thank you. So, Annette, do you want to introduce our speaker, today's speaker?
Our first speaker today is Dr. Gavin Sachs, a researcher and professor from Cornell University, and he is going to speak to us today on the chemistry of storing wines in cans. Welcome, Dr. Gavin Sachs, and please tell us a little bit about yourself and start your presentation.
Great. Thank you, Annette, and thank you, Esmail, for the invitation to speak. I'm going to do that awkward transition that everyone has to do during Zoom where I struggle to share my screen and say a lot. See, told you. And there's no graceful way of doing this as I search for it. So I have not had the pleasure of being in Michigan for several years. I think the last time I was out in the wine regions of Michigan was 2002. American Society of Enology and Viticulture Eastern Section had a conference in Traverse City. It was wonderful. Got to tour the Leelanau Peninsula, and regrettably, I've not been back since to enjoy the area. And unfortunately, it looks like it may be several more months before that could happen. Okay, so when I was speaking back then, I think I spoke on accumulation of flavor compounds in Riesling. I most certainly was not talking about canned wine. I'm not even sure if I knew that canned wine existed at that time. It was not on my radar. And things have changed. So this slide's a couple of years, sorry, this infographic's a couple of years old. Canned wine, however, still continues to be the fastest growing sector of wine packaging. It's pretty easy to be the fastest growing anything when you start from near zero. So this is, of course, on a percentage basis. A couple of years ago, percent share of wine sales was a couple tenths of a percent. Last I checked, it was, depending on whose report, I believe, somewhere between 0.5 and 1%. So still small, but still growing. And this is not just for wine, but also for some other fermented beverages as well. Of course, beer, but also things like cider. There's interesting canned kombucha and other canned beverages. And there's a number of reasons for this. Perhaps the biggest reason is consumers want it. But then from why they would want it, it's lightweight, it's strong, that's good for shipping, that's good for the consumer, especially if they plan on taking their wine into areas where glass bottles are not appreciated, pool parties, camping, stadium events. Overall, cans have a pretty good sustainability track record. Plastic certainly can be recycled, but it gets downcycled. It's less valuable every time it gets recycled. Glass can get recycled, but it's also energy intensive, and it takes a lot of energy to move glass around. Aluminum, there's a strong domestic industry for recycling aluminum, and it's been in place for decades. So aluminum not only can be recycled, it does get recycled, and the product that gets recycled is as good as the original. So considerable interest, not just in amongst wine producers, but more broadly in the beverage industry about trying to transition certain products that were glass packaged or plastic packaged into aluminum cans. I was doing some furious Googling last night to see how many Michigan producers are currently canning wine. It looks to be more than a few. In fact, I saw at least a couple that received accolades and awards for their canned wine products. So I'm assuming that the situation is similar to New York, where within Michigan, there's growth and there's interest. So even if you are not a producer who's yet putting a wine into can or a cider into can, it may be on your radar that you might want to do that for certain products. I think that's probably the typical experience in New York. We have a couple of wine producers who are doing nothing but cans, some cider producers doing nothing but cans. For most producers, they expect to have maybe one or two of their offerings go into can, so that they have that for a particular product, for a particular kind of consumer. They'll take advantage of custom canning operations, mobile canning operations to achieve this. And so the questions that I get most often, both in New York State, but also more generally amongst US producers, is, okay, I want to put a wine in can. Will this particular wine be okay with this particular manufacturer? Which liner do you recommend? The manufacturer is telling me they can't guarantee performance. What does that mean? If I want to produce a wine that's going to be more compatible, is there anything I can do? Is there anything I should be careful of, look out for? And finally, what shelf life can I get before there would be a loss in consumer acceptance? Before there's some sort of problematic change to the wine. I'm not sure I'm going to be able to answer all of these concretely, but I can tell you the way that our lab group, and more specifically a couple of my grad students, are trying to answer these questions right now. So, okay, getting started. The science of aluminum cans, the science of technology of aluminum cans. A can is not actually a can. It's a plastic bottle. See, right there. You can take, if you want to try this at home, you can take an aluminum can, expose it to either strong acid, or in this case, it was a strong caustic, a strongly basic solution. You can etch away the aluminum and reveal beneath it this super, super thin plastic liner that's been sprayed on the inside. So we call it a plastic bottle, but it's 1/100th of the thickness of a typical plastic bottle like you would have for like, I don't know, a carbonated beverage. The thickness of this liner might be only a few microns thick. So it's like it's wafer thin, or thinner than a wafer. This liner protects the wine from the aluminum and vice versa. Or for that matter, protects any beverage. I don't know of any beverages that aren't produced in lined aluminum. And that can liner historically would have been made out of a BPA-based epoxy. You can still find these, but there's been a transition away from using BPA-based epoxies to using other types of epoxy, or epoxy acrylic blends, or acrylic, or polyester. Generally, as a producer, you don't necessarily even know what kind of liner you have, even if you ask. It may be hard to get that information from the major can producers, other than to know that it is or is not BPA epoxy. It might be called BPA non-intent. That is, they don't intend to have any BPA present. But on the market right now, most of the things that we've seen are either epoxy, non-BPA epoxy, or epoxy acrylic blends. Acrylic does exist. They are, quite frankly, dreadful for wine applications. Let's see. Oh, also, as we go on, I'm not sure if this was officially announced, but if you have any questions, please drop them into the chat or, pardon me, into the Q&A, I think, and we'll get to that at the end of the talk. Okay, so taking a step back, this slide, this is the generic slide that I give to students in any kind of food packaging lecture or flavor chemistry lecture. This is not canned wine specific. When we talk about the effects of packaging, there's the big three categories of how can this packaging affect flavor. Okay, number one, degradation. That is ordinary changes that would happen to the product if there was no package. So as an example, if you don't put a wine into a sealed container, it'll oxidize. And that's a form of degradation, oxidation. So there's nothing specific that is happening as a result of the container. Rather, the container is slowing these processes. If the container fails, then it would allow these processes to happen faster. So, for example, if you're canning a product and you've got a bad seam, then it would degrade faster. And so the main concern with non-microbial spoilage and canned wine products would be oxidation. And so there's a lot of work that's been put into determining best practices and maximum tolerable oxygen pickup and ingress for canned wine products. It's been adapted from the brewing industry. Okay, so when you package a wine, you don't want to have lots of oxygen. Number two, scalping. Taking a step back, this is plastic on the inside. Plastic is nonpolar. Like dissolves like. And most flavor compounds, especially most odorants, are nonpolar. So this would be no different than if you have an oil-water mixture, the oil would absorb some of the nonpolar flavor compounds more than the water. If you package a wine, you run the risk of having scalping whenever you have plastic present. Overall, this does not seem to be a major issue for wine. Wine does not contain very polar compounds. If it, whatever it would have had from the grape tends to actually get absorbed onto the lees or the inside of barrels, such that it's no longer still around by the time you package the wine. There's a couple of exceptions. One is if you have cork taint in the wine somehow. Maybe you had tainted bentonite. That or other fining agents that had cork taint aroma compounds. Those are very nonpolar. Maybe that would be a bad thing if they can remove those. As an aside, where this is a bigger issue for fermented beverages are things like dry hop beers or any beers where you're adding essential oils late in the process, because those tend to be very nonpolar. They're added late, after fermentation usually. I understand that some of the major breweries will have two different formulations, one for their canned product and the other for, well, at least based on the label, looks like the same product, but their product going into glass because they expect different levels of scalping to occur. I know the big soda companies do the same. Okay, finally, and this is what a lot of the talk is going to be on today, tainting. That is flavor changes that are a result of either absorption from the beverage or reaction of the packaging with the beverage. These are things that would only occur as a result of the packaging being present, that specific packaging. So this is different than degradation, where these are processes that would occur in the absence of the packaging. Tainting involves changes that happen due to the packaging, usually due to reaction with it or due to absorption from the packaging. So if you, as an example, if you have cardboard and you store some sort of food in that butter, and the butter takes on cardboard type aroma, that's an example of tainting. Okay, so we'll talk more about that. And the big issue with tainting and fermented beverages, particularly wines and ciders, is formation of hydrogen sulfide. that is a key aroma compound found in rotten eggs and in rotten egg smelling wines. And this is well known is probably an exaggeration. It's been known for some time that this arises from, or is formed from free SO2. And what makes wine and cider distinct from most beers is that they have added to them SO2 intentionally. Beer will have a small amount of SO2 present from fermentation. Occasionally, producers will add a tiny amount, although that's not too common in the United States. Wines and ciders routinely have SO2 added to preserve some of their characteristic aromas. This is documented in literature, mostly in the patent literature. It's pretty easy to demonstrate. You can just take cans of that would be used for wine, add a model wine solution, so water, ethanol, adjust pH, add SO2, and you will produce variable amounts of H2S depending on the particular can and the particular liner. Sensory threshold of H2S, quite low. 1 microgram per liter, that's a part per billion. So it doesn't take too much conversion of parts per million levels of SO2 to yield parts per billion levels of H2S. Okay, there'll be more about this. As an aside, one of the things we worked on in our lab is to try to come up with a more convenient way of measuring H2S in the winery. Currently, winemakers' approaches to measuring H2S usually involve the sniff-it approach, which is good as a qualitative tool. If you want to know the effects of treatments, you want to know how bad things are, you want to document differences, then it sure is nice to be quantitative. You can send things out for analysis to commercial labs. This is challenging to do without losing the H2S, either due to volatilization or due to oxidation, such that by the time the sample shows up at the testing facility, you may not have any H2S anymore. Much nicer, much easier, much more accurate to actually do the measurement in-house. And so we have something we're preparing and about to publish. It shows how you can adapt an AO unit, just like you'd use for measuring free SO2 in the winery, and use these H2S gas detection tubes that were developed initially or originally for the mining industry. And they can be used for environmental monitoring. Turns out they also are appropriate for quantifying H2S in wines, either from tank or from a can or from a bottle, and get well below sensory threshold and do it in a reasonable amount of time for a reasonable price. So I'll have more on that, and my students will have more on that in the hopefully next month or two. We'll have that out. Okay, so more on H2S. The only source of H2S in wine is not SO2. In fact, that's an unusual source. It's well established that you can have a wine and it goes into a bottle, and then after some amount of time, it comes out stinky. And that stinkiness is, at least in part, for most wines, due to formation of hydrogen sulfide during anoxic, that is, minimal oxygen storage. And that will happen even in glass packaging. Could happen in tank, for that matter. And so there's been several odorless precursors that have been identified. This includes copper sulfide complexes. If you have a wine, you might be thinking about this right now. You've had a wine that's had H2S form or some other sulfurous off aroma. You're legally allowed to add copper sulfate to try to remediate those sulfurous off aromas. And copper will form non-volatile complexes with H2S and other sulfurous off aromas. That's great, it does it. One of the problems is that most of those copper sulfide complexes do not precipitate out. They will if it's just water or just water and ethanol, but in a real wine, some of the other wine components inhibit that precipitation, which means that copper sulfide complexes, they're all just sitting there in your wine. I think there was an estimate from a group in Australia suggesting it was well over 90% of that added copper stays in the wine. So there's treatments that can be used to try to remove that copper. There's some synthetic polymers that are good at complexing out that copper. Yeast lees probably will do some removal. but do not make the assumption that any added copper has precipitated out. Make a measurement. Another potential source, polysulfides. This can come about by oxidizing wine, or if you have any elemental sulfur present in the grape must, it will make not only H2S during fermentation, it will also make soluble precursors, no aroma, odorless, but that can slowly degrade during storage of the wine to release H2S. Okay, what I just listed, 1A, 1B, this is true for all wines, all packagings. All you need is anoxic conditions, and you don't need a can to cause this release. What we're going to be focusing on is another source of H2S, which is reaction of aluminum with H2S. So what you can do, if you want to play around with this experiment, take a piece of aluminum foil, take a glass of wine, put the aluminum foil into the glass of wine. If it's a normal table wine, it's got some SO2 in it, cover it up. You don't want a lot of headspace. Come back. Don't do this to a wine you're really hoping to drink. It's going to render it unpalatable within a day's time. It will start belching out H2S. This is not a very hard reaction to demonstrate. Oops. Okay, so let's see. And when you do this, you take aluminum foil, you put it in the presence of, in this case, a model wine solution, but you can, and SO2, you can have both release of H2S, but you can also see, at least at a neutral pH, formation of blisters on the aluminum surface. These would dissolve at wine pH, but eventually, given enough time, you would actually get pitting and a loss of the hermetic seal. That is, the can will just completely corrode and possibly start leaking, which is a terrible situation to be in if you're a can wine producer, because it leaks out, gets onto the can below it. The outside of the can generally is not lined, which means it will corrode through that. Process repeats. Okay, so SO2 plus aluminum equals H2S. And pitting, and these reactions are reasonably well known. Aluminum can both react in aqueous conditions, and this is promoted in the presence of either strong acid or strong base to make aluminum hydroxide. It can also react with SO2 to yield H2S. And it appears that this first reaction, formation of H2S from SO2, helps promote the second reaction. We get more overall aluminum corrosion when SO2 is present, even at the same pH. Okay, and this reaction's been known for some time. In fact, the earliest report I can find in the literature on it goes back to just after Prohibition. People were trying to figure out what tanks to use for wine. For those of you who know your wine history, that's Lyman Cash of Cash Still fame, who was the lead chemist at Gallo, who showed pretty convincingly that aluminum, when put in the presence of wine, will start releasing H2S. Okay, so aluminum reacts with SO2, makes H2S. But this shouldn't be a problem, right? We've got a can and it's lined on the inside. The liner is supposed to protect the can from the wine and vice versa. So before we go any further, I want to do a quick review of the role of SO2 in wine. There's a couple reasons for this, but one is to talk about what we think is going on with SO2. The other is to explain why we need SO2 in a wine and why it's so hard to eliminate. Okay, when we say SO2 in wine, we're really talking about multiple species, multiple chemical forms of SO2. There's SO2 as SO2, what's also referred to as molecular SO2, this neutral species, S bonded to two oxygens. This is in equilibrium with bisulfite, and this bisulfite's the major form of SO2 in wine. Combination of molecular SO2 and bisulfite is referred to as free SO2. Again, most of this free SO2, bisulfite. And then we also have this other form bound SO2, which is the combination or adduct of bisulfite with other compounds in wine to make a new covalently bound chemical structure. This bound SO2 is less active in wine than free SO2, but if you drink it, it will dissociate in your stomach. So from a health standpoint, it's just as active as free SO2. So it gets counted as part of what's referred to as total SO2, and that's what's regulated by most governments. Okay, so molecular SO2 is a small fraction of free SO2. The proportion of SO2 in wine that is molecular is dependent on pH. The lower the pH, the more molecular SO2. This is why, as a winemaker, it's common to use these charts where you measure your pH, you measure your free SO2, and then you've got like a lookup table or maybe an equation, and you calculate molecular SO2. Lower pH, higher proportion of molecular SO2. Higher pH, you have less molecular SO2. So the reasons why we have SO2 in wine. Number one is it is a broad spectrum antimicrobial. And specifically, the molecular form of SO2 is a broad spectrum antimicrobial. It's active against a wide range of yeasts and spoilage bacteria. Depending on whose enology text you're reading and the particular wine you have. For table wines, typically somewhere in the ballpark of 0.5 to 0.8 milligrams per liter molecular SO2 are recommended, with higher levels in sweeter wines where yeast spoilage would be of greater concern. Yeast are a little more SO2 tolerant. Lower levels for dry wines where bacterial spoilage would be of greater concern. Okay, so that's one reason. Another reason, SO2 is an extraordinary antioxidant. In fact, it is the strongest antioxidant based on reduction potentials, the strongest antioxidant you are allowed to add to any food or beverage. I know that things like resveratrol and polyphenols get all this attention and vitamin C. No, free SO2, let me put it another way, SO2 in general, that is the strongest antioxidant by far. Otherwise, we could just use vitamin C and polyphenols as our antioxidant. But no, free SO2 is the strongest antioxidant we can add to any food or beverage, which is critical for preserving the freshness of those fresh aromas that we expect to get from red and white wines, and particularly from white wines. Okay, so common recommendations for table wines, again, pick your favorite. Enology text, typical recommendation is 30 milligrams per liter free SO2, maybe as low as 20, maybe as high as 40. There are most certainly wineries that successfully produce wines with no added SO2. Those will typically be making a different kind of wine than what people might be expecting from a wine that has SO2 added. Once wines have less than 10 milligrams per liter free SO2, then oxidized aromas start to become apparent in wines. It's a little bit higher threshold for whites, a little bit lower threshold for reds, but at some point, as free SO2 drops, oxidized aromas become apparent. Okay, so that's free SO2, that's molecular SO2, bound SO2. So if you add SO2 to a wine, what form? Maybe you add it as potassium metabisulfite. Maybe you use a solution where you've bubbled a SO2 gas, but you've added in some way. The amount that you add does not show up in your free SO2 if you then take an immediate measurement. If you tried to add, at end of fermentation, you tried to add 50 ppm free SO2, what would you get? Maybe you'd measure 25 free, maybe you'd measure 20 free, 30 free. You wouldn't be measuring 50 free at the end if you just added SO2 at the end of fermentation. So there's a number of binders in table wines. In sweet wines, glucose can be a major binder. In red wines, anthocyanins can be binders. You can have oxidized aroma compounds like aldehydes, for example, methionine, which is the smell of baked potatoes and soy sauce. And quantitatively, major binder in most wines is a compound called acetaldehyde, which you would find in high concentrations in wines that don't have any SO2 added. For example, sherry type wines, Madeira. It's the smell of, well, sherry and bruised apples. It's a very strong SO2 binder, such that if you have a wine and it has any free acetaldehyde, and you start adding SO2, you will not be able to measure any free SO2 until you've completely or nearly completely bound up all of your acetaldehyde. Okay, so we've got stronger binders, we've got weaker binders. And the strongest binder is by far acetaldehyde, and then it goes up from there. If you add SO2 to a wine that has these compounds free, you will then make new chemical species, glucose bound to SO2, anthocyanins bound to SO2, and so on. Okay, so what happens as a wine oxidizes is that as far as we can tell, until a wine is horribly oxidized, you don't make de novo new flavor compounds. Rather, what happens is SO2 will react with some of the initial oxidation products. Oxygen comes in, it reacts with things like polyphenols, will make hydrogen peroxide. SO2 will react with those oxidation products, and then some of the bound forms will re-equilibrate and release free SO2, and at the same time release some of these oxidized aromas. And once you get below around 5-10 milligrams per liter free SO2, you start to notice these oxidized aromas again. My experience with winemaking is you freshly ferment a wine, and a newly fermented wine before any SO2 is added often can smell kind of oxidized. And you get it off the lees, and you smell it, it doesn't smell quite right, and you put a little SO2 in. And to use the parlance of winemakers, it cleans it up. What you're doing is you're binding up some of these oxidized aroma compounds. The reverse process happens as the wine oxidizes. So this is one of the challenges with limiting SO2 in wine. There's a number of products out there on the market that will talk about trying to replace SO2. Oftentimes they're focusing on antimicrobial activity of SO2. Most certainly you can can a wine or bottle wine without SO2 and avoid microbial spoilage. The brewing industry does this. They have solutions, but the harder part. So what are the solutions? You can sterile filter, you can use Valkyrin, DMDC, pasteurize. There are pasteurized wines out there. There's lots of strategies for avoiding microbial spoilage. The problem is avoiding the aroma compounds that will be released once free SO2 gets below that 10 milligram per liter or so level. And there are many styles of table wine where you will either have loss of some of the key aroma compounds or masking of those key aroma compounds due to release of those aldehydic off aromas. We do not yet have an alternative scavenger of, in particular, hydrogen peroxide, which is one of the reaction products that forms when oxygen comes into wine. Ascorbic acid does not rapidly react. Glutathione does not rapidly react. Polyphenols do not rapidly react. What rapidly reacts? SO2. So that's the problem. How do we prevent either formation or release of these aldehydic off aromas if we don't have free SO2? And the answer is, I don't know. You'll make a lot of money if you can figure out a way. Okay, so that explains why it's challenging to completely eliminate free SO2. It has nothing. It is not because of the challenges of replacing the antimicrobial effects of SO2. It's the challenge of replacing the antioxidant and off-aroma binding capacity of SO2. So this dependence on free SO2 probably helps explain why we don't have H2S reported in canned red wines, but we do sometimes have it reported in canned white and rosé wines. So in our own work, we've done some preliminary studies, and we've yet to find a red wine that in a canned wine trial study will evolve large amounts of H2S. I have heard of a couple of cases on the West Coast involving Pinot, but it seems to be pretty unusual. Okay, so the reason we think this is, there might be a couple of things. One is it could be the polyphenols in red wines, anthocyanins, tannins, are somehow passivating the surface of cans and preventing reaction. There's another factor, though, which is, and here's the dirty secret of SO2 measurements. All current strategies for measuring SO2 in wine badly overestimate how much free SO2 is in a red wine. A typical red wine has no more than 30% of both the molecular and the free SO2 that your AO or your Ripper or your FIA says that it does. And the reason is that all of these standard approaches for measuring SO2 involve a dilution step and an acidification step. That is sufficient to decompose those bound anthocyanin bisulfite complexes. You end up measuring your bound SO2 that's bound to anthocyanins using all standard methods. So the amount of SO2 that's in red wines is, generally speaking, much, much lower. The one exception we find occasionally is for Pinots, Pinot Noirs, probably because they have lower tannin, lower anthocyanin. But most red wines with typical levels of anthocyanins don't have this, have plenty of SO2 binding capacity, and as a result, the wines have much less free and molecular SO2 than expected. Okay, not expected, pardon me, than what the tests say they do. Okay, so this brings us back to this initial diagram and the problem. We have this liner. Why isn't it doing its job? And how is SO2? And in what form? Is free SO2, is bisulfite, as molecular, or all forms, including total SO2, bound SO2 involved? How are these getting through the liner and to the aluminum layer? We also have, I didn't mention this, but we also have this passive layer of aluminum oxide that forms spontaneously on aluminum. So when you touch a piece of aluminum foil, or that's an aluminum can, you are not touching aluminum metal, technically. You are touching aluminum oxide. And this passive layer also provides some level of protection. So how is this happening? There's a few hypotheses, and these are not mutually exclusive. One is that the liner has imperfections in it, maybe pores, maybe thin spots, in which case it could allow bisulfite to pass through. Does molecular SO2, which is volatile, when you put your nose into a glass of wine, it has too much SO2 and you smell and it burns, what's doing the burning is the molecular SO2 form, because that's the volatile form. So is SO2 able to diffuse through the liner because it's volatile? There are published diffusion constants for SO2 through a wide range of plastics. Or does SO2, or in the form of bisulfite or SO2, react with the liner and degrade it, which then creates defects that allows either bisulfite or SO2 to make it to the aluminum? Very preliminary work from our group. We think the problematic species is likely to be molecular. But we're still not sure actually if this is because you get higher molecular at higher pH. We can't yet determine if this is because it's a synergistic effect between low pH and higher free SO2, or if it's actually due to molecular. But molecular may end up being the better predictor of failure than free SO2. Oops. Okay, so this is one question that our group is trying to answer right now. It's not the only question. Beyond how does SO2 get through the liner and through the alumina? Another question we're trying to answer, what other wine components can either exacerbate or mitigate hydrogen sulfide production? The major producers of cans and can liners will have these laundry lists of compounds that they say are problematic. If you ask them where they got those recommendations from, they're really not sure. as far as I can tell, what happens is they will have a potential problem, or they'll try to glean information from other studies on other products. They'll find problems with copper in some other product, and they'll assume it might cause a problem with canned wines too. And they'll err on the side of caution. Or they'll use accelerated aging tests that are based off of corrosion in the presence of sodium chloride, which may or may not be relevant for the kinds of corrosion we care about, which is H2S production. Okay, so there are still these lists: recommended values for pH, recommended values for ethanol, copper, chloride. I've seen recommendations for tannins on these lists. It is not clear where these recommendations came from, and it's pretty obvious that they haven't been validated. So this is something we're interested in doing, is establishing what are appropriate limits for defining risk. Some of these make some sense. Chloride is known to corrode bare aluminum. Copper can facilitate electrochemical reactions. But what about in a real canned wine where there's other compounds present that can, say, decrease the activity of these species? Are they still relevant? So something else we want to work on. And then finally, where we want to get to eventually is empirical tests that are validated for what we care about. Current tests, I say it right here, they are validated for overall corrosivity. Generally, it's how much aluminum will dissolve from the can into the wine. As a wine producer, that's important, but that's for predicting overall corrosion. The production of H2S is not all that well correlated with total dissolution of aluminum. What we care about is loss of quality. How much H2S will I produce? Because that happens far quicker than can corrosion and a loss of can integrity. So we want to validate these tests for H2S production and eventually develop a valid bench test that either a winemaker can use or a can supplier can use or both can use to rapidly, how rapid, I don't know, a day's time, a couple days time, predict whether or not a product is going to have long-term issues over, say, 6 months time to a year time. Generally, right now, where people say, so what's the longest shelf life? Most producers I've spoken to have not been able to achieve shelf lives for typical table wines with normal levels of SO2 for whites and rosés much longer than 6 months. The worst I've ever heard of for certain liners has been as little as 2 weeks. But typically 3 to 6 months seems to be the standard shelf life people are achieving. But there's some error bars associated with that. And there's some products that seem to fail very quickly and some that will last for longer. And clearly as a producer, you would like to have something beyond just average likelihood. You'd like to know for a specific product, what should I be able to achieve? In part because that will tell you maybe how much wine can I can out right now, one canning run, as opposed to dividing it up into like 3 or 4 different canning runs. Okay, so lastly, something we're working on to try to achieve this. We've been working with some of the some of the beverage can producers and some of the liner producers to develop accelerated aging tests based on coated coupons. So these are pieces of aluminum metal coated with the commercial liners. We've been developing appropriate protocols where you can incubate these in glass with a small amount of wine at elevated temperature. This is great for testing individual wines. The other thing we're doing is we're taking model wines with defined compositions, varying pH and SO2 and both molecular and free SO2, chloride, copper, ethanol, whatever else you're thinking about. You're making a flavored wine, maybe we can throw in that flavoring agent. And then we can then assay at the end of a day or two's time, storage for H2S production, for aluminum dissolution, for off aromas beyond H2S, for visible pitting, and so on. And we're also doing experiments where we're validating this against long-term can wine storage. Okay, so hopefully you have been able to get something out of this. Hopefully I also didn't, if you haven't done canned wines yet, hopefully I didn't terrify you. I think canned wines are wonderful. I buy a lot of them. There's some very successful, very tasty products on the market. But there's a point of caution, which is the use of SO2. SO2 is used in table wines routinely as an antimicrobial antioxidant, and the antioxidant role is hard to completely replace if you want to achieve certain styles of wine and have certain shelf life for that wine. You can go the brewing approach and put a best by date that's 1, 2, 3 months after the product goes into can. Most winemakers don't want to do that. SO2 can somehow get around through whatever it's doing, gets past the liner, reaches the aluminum, and produces H2S, and also causes corrosion to the aluminum. So what to do in the short term? The main thing I recommend is to think carefully about what your free SO2 target is. If you're using just as a rule of thumb, I'm always going to target 30 milligrams per liter SO2. Why? Why are you doing that? Are you doing that because you've always done it that way? What I recommend doing, especially if you plan on selling this product within a year's time, and you're putting into a can is hermetically sealed. The amount of oxygen that gets into a can post-canning is almost unmeasurably small, which is why the brewing industry loves them. Part of the reason why people target 30 is because with traditional cork packaging, you expect some air to get squeezed out of the cork into the product, and you're going to have air in the headspace. And sometimes if it's a lousy cork, you can have leakage, ingress of oxygen into the product after that. You may be able to get away with as little as 10 to 15 milligrams per liter of SO2 after accounting for any oxygen pickup that occurs during packaging. So let that oxygen react with the SO2 in the wine. If the resulting SO2 is in the 10 to 15 range, that's going to be enough in most cases to still bind up some of those malodorous oxidized aroma compounds. Molecular SO2 probably matters more, or is a better predictor. We're still trying to figure out what the role of other components is within wine. And this leads us to future research, which is we want predictive tests that predict not just overall corrosion, aluminum dissolution, but H2S formation. Existing tests, by and large, are not validated. And this brings me to my concluding slide. Thanks to Luna Mazal-Bendik, who is a visiting scientist, Rachel Allison and Austin Montgomery, who are currently PhD students in my lab, and several funding sources and industry cooperators. And thank you again to Esmail and to Jennifer for facilitating this conference and inviting me to speak. And there may be time for a few questions.
Thank you, Dr. Sachs. Thank you so much.
Oh, by the way, I was looking at the comments. Melanie, I too wish I got that cookie. I'm not sure why they didn't make it out here. This is outrageous. That's like the only honorarium I would have appreciated.
So,
okay, go ahead. I'm sorry.
Yeah, I said thank you so much for your time, and this is amazing. It was very good information and presentation. Thank you so much.
Mm-hmm. And I see there's a question from Gino Venditti. Have you used SEM, scanning electron microscope, to look at a cross-section of a compromised can to determine which mechanism might be occurring, damage versus chemistry to the compromised protective layer inside cans? Yeah, thanks, Gino. We are doing that right now. SEM, for those of you who are familiar with the technology, think of this as a microscope that's going to, instead of getting down to seeing things at the micron scale, which is what a typical light microscope could do, go several orders of magnitude smaller than that, down to the scale where you get close to not quite, but very close to atomic resolution. And you can get information on how the chemistry of the surface has changed. Yep, this is one of the tools that we're using right now. In fact, most of the can manufacturers are using this already to look at the damage that occurs following storing wine in cans. The challenging part we really want to look at is the damage to the liner. This is a little more technically challenging because looking at a liner in cross-section, if that liner's microns thin, it's doable. It's requiring us to rely on expertise that we have elsewhere at Cornell. So the short answer is, yep, that's one of the tools that we're using to try to better understand the mechanism of how can failure is happening. Okay, should I keep going through Q&A, or would you prefer to read questions, Esmail?
There's the other question in Q&A.
Okay. Yeah, I see. I see. There's some things coming in the chat, some things coming in the Q&A. So I'll go for the next Q&A. Casey, can you touch on low pH wines? Could acidity alone cause issues as a result of SO2 interaction? Thank you. Low pH, I think, is an exacerbating factor, but keep in mind, Coca-Cola, pH 2.4, and it uses a thinner liner than wine, and it doesn't have any problems. This is not just a pH only issue. It is also not an acid only issue. We can store wines that have no SO2 in them and not have any problems. The problem seems to be a combination of pH and SO2. And if you don't have the SO2 present, you don't have those pH issues. You can put plenty of low pH products like carbonated sodas into a can with no problems. And my suspicion of the effect of pH is, I had two possible explanations. One is that lower pH means more molecular SO2. Molecular SO2 is the active species that's getting through the liner. The other is that SO2 is damaging the liner. And then once that damage occurs, low pH will more rapidly degrade the aluminum. So the low pH causes problems once the liner has been damaged. It's a symptom rather than the immediate cause, or a secondary effect rather than an immediate cause. And I see, I'm going to go to the chat next and then come back. Oh, great. I deserve a cookie. I agree. So I will have to see if there's any cookies in the house when this is all done. What is the average shelf life of red wine? I presume that you mean within a can. So I don't have any wines that I have looked at here at Cornell, since we are still relatively new to actually getting things into can and setting up our canning operation. Industry collaborators have sent us wines, red wines that have been in can for over a year, and they seem commercially acceptable to me, and they consider them commercially acceptable. That's not all of them, but that's at least some of them. One of the things I would say in general is that there's a lot less data on red wines in general, because more wine producers are more commonly put whites and rosés into can than reds. Reds tend to be higher value. There's still I think a ceiling for how much you can charge for a canned wine, which means that there's a bias towards using less expensive whites and rosés. But in talking to producers of red wine, they can routinely get definitely over 6 months shelf life, longer than a year shelf life out of reds. But the biggest canned wine producers of reds are canning on demand. They're not canning out they're not doing it like a wine where they can once and then hold on to all that canned product for a year and the next vintage. No, they would have a canning operation, and then they would can for, just like a brewer would. You can for 2 months need, 3 months need, put it out, do it again. So a number of the larger canned red wine producers aren't anywhere near that experience. I was speaking to someone from E&J Gallo. They don't have any issues. That was their solution, was we don't have any issues anymore because we just basically treat it like a beer. We can on demand. I was talking to a large cider producer. Same strategy. We get that product sold within 3 months' time. That's a strategy. That may not work quite so well depending on your distribution model and your access to mobile canning lines, assuming you're not canning in-house.
Perfect. So I have a question for you. How about the sparkling wine? Is it okay to use, canning? Technically, I think it's possible.
Yeah. So canned sparkling wine works well. There's a few comments about that. Number one is carbonated products clearly have a track record. I mean, we have carbonated sodas and carbonated beers. Carbonation's more helpful in one way, which is that because you've got CO2, it tends to make headspace control a lot easier. So you have less oxygen pickup during canning. One reality is that it's harder to achieve high atmospheres. So if you want to have the same level of CO2 that you would have in a method champenois type product, 6 atmospheres, it's hard to achieve that with most canning lines. I understand there's people doing work on this right now to figure out how to get more pressure, but brewers don't package their products Sodas aren't packaged with as much CO2. Wine, sparkling wine, not the Champion Wall style wine, has much higher levels of dissolved CO2. So that's the one sort of challenge. The other is if it's a white or rosé, you've got SO2 most likely. You're still going to have problems with H2S formation, or I should say potential for H2S formation.
Dr. Sachs, there is another question in the Q&A.
Oh, yeah, I see another one from Casey. Thank you, Casey. You've been prolific with your question asking. Ball has actually been good with telling me what generation of cans they're getting. Good. I'm not sure if they've been telling you what type of liner it is, but they'll say like Gen 1 versus Gen 2 type liners. Yeah, so basically the terminology, this is very crude, is you have the traditional can liners, and within those, usually there was 3 levels of thickness for the can liners. There was the thin layer, which I think is the brewers used. You have the medium thickness, which I think soda uses, and then you've got the thickest layer, which is often called like the energy drink level of thickness. That's the thickest liner. That's usually what's recommended for cans. Historically, that was BPA epoxy. Gen 1 was a replacement for BPA epoxy. Those were often acrylic based. They were dreadful. When I talked about people getting 2-week shelf life, I think what people are debating is were they just were they just mediocre or were they truly bad? But generally, the Gen 1 liners, I don't even know if you can still get those. If you can, I would not recommend them. There's Gen 2 liners now, which are an improvement over the previous Gen 1 liners. Crown's got their version, Ball has their version. Those are the 2 main suppliers in the US. And their performance is by and large better. They both still have occasional issues, and they will make recommendations. And so a lot of the things I said regarding getting 3 to 6 months shelf life on average, that's based on the Gen 2 liners. I would encourage you right now to ask whatever supplier you're using. Sometimes people don't talk to the supplier directly. They'll talk to their mobile canning operator, who will then source the cans. Ask what's currently recommended for best performance, longest shelf life, and minimal off aromas. And the other thing is there is still BPA epoxy. If you're not selling in California, you don't need to worry about putting that warning label saying this product contains BPA, which is and there's a big long warning. We have producers in New York that are still using BPA-based epoxy liners because they don't plan on distributing outside of New York State. Okay. Was there another question? I don't know where maybe I just answered the last of them.
I think that's all we see. Is there anyone else with a question for Dr. Sachs? There is a comment. Dr. Sachs,
thanks, Nikki.
Thank you for your clarity and scientific honesty in your presentation.
Thanks, Tom. I'm assuming all these people are real and just aren't like, bots that you've created to make the speakers feel good. But you can never quite tell with these Zoom things. But I hope I have the opportunity to meet every one of you at some point in person at a future Michigan event. Like I said, it's been almost a decade now since I've had a chance to at the tour Michigan. I'm sure it's changed since I last remember it. And it was wonderful during my last visit.
Yeah, Dr. Sachs, that was just excellent information. So we'll be sure to share it with our Michigan producers.
Great.
So Ishmael.
Yeah, thank you so much. I didn't see any question. So thank you so much. I appreciate your time.